podcast is brought to you by LMU Munich.
Okay, thank you very much for the opportunity to speak at this wonderful conference. What I want to tell you about is some work that's been done over the last several years by a group of people that are somewhat on the fringes of string theory, working on the basic idea that eternal inflation is the key ingredient in getting predictions out of string theory. Now, I have to say it makes me a bit nervous to summarize what I think is a good body of work in 25 minutes for a somewhat skeptical audience. But I'm just going to give my personal view of where I think we are. And I think that this is a good time to summarize, because we've had some successes, but also, in my opinion, some shortcomings. And I think there's a need for new ideas. And I'm hoping that some of those will come from you. First of all, the question of how, in principle, to get any kind of observational prediction out of string theory in the context of the landscape is a crucial question. Can we make some prediction for the SUSY breaking scale or the non-Gaussianities in the CMB? What, in principle, is the technique for doing that? And if you have an idea, you should get in touch with me, because this is my job. It's my job to talk to astronomers and people who look for dark matter and high-energy experimentalists as part of the Scarpa Institute. And while my job is not a legitimate string theory job and requires talking to these people about what predictions string theory might make, we do have a job opening for a legitimate string theorist at any level. And if you're finding that it's a little too hot and sunny where you are, I can assure you that we don't have that problem in Amsterdam. Coming to the science, we observe a positive vacuum energy. String theory seems to give us a vast landscape of metastable four-dimensional vacua with positive and negative cosmological constant. Of course, this is far from rigorously described so far, but the simplest explanation based on the known data is that we are in a vacuum with positive cosmological constant. Now, as long as string theory contains at least one vacuum whose decay rate is smaller than its Hubble expansion rate, then, starting from a finite initial volume in this vacuum, eternal inflation will produce an infinite space-time volume in the false vacuum. The false vacuum can decay locally to any other place in the landscape, but globally, the false vacuum will never completely decay. And so even if you start out in your favorite vacuum, the landscape will be populated dynamically. The terminology that's usually used is that the vacua of string theory are realized as pocket universes inside the eternally inflating multiverse. Now, there's a question. If string theory has such a rich landscape of compactifications down to 4 dimensions, how can we make predictions? And the proposal is a very simple one, that we should make predictions by counting the relative abundance of different types of events in eternal inflation. If you want to know the probability for an experimental outcome to be A or B, what you should do is count the number of events A and B in the multiverse. So, if you want to know the probability of finding supersymmetry at the LHC, you can focus on regions in the multiverse that agree with all of our known data. So you can focus on places where there are LHCs, and just count how many LHCs find supersymmetry and how many don't. Now, of course, when I say it that way, it sounds a little bit ridiculous. I see that I've amused certain people here in the front row. But for certain quantities, not for counting LHCs, we can actually make enough guesses and reasonable assumptions to be able to compute these probabilities. And one of the crucial questions is whether we'll be able to extend that to make more predictions. Now, there's good news and there's bad news. The good news is that this quantity that I want to compute is independent of the initial conditions. This is because the dynamics of eternal inflation has an attractor behavior, and at late time, the number of events of any type is controlled by this attractor behavior. The bad news is that this ratio depends quite sensitively on the choice of time variable. So the characterization of the attractor behavior is ambiguous. Semi-classically, that's the end of the story. The theory is diffeomorphism invariant. There is no preferred time variable, and NA over NB is just not well defined. Doing various things like computing it more quantum mechanically, doing perturbative quantum gravity, is not going to change this. As long as you're dealing with the theory with diffeomorphism invariance, NA over NB is not going to be well defined if you're using a global description of eternal inflation. So why persist in trying to compute this quantity? The reason for hope is that the reason the ratio is ill-defined is because, of course, the number of events of any type in eternal inflation is infinite. But the reason it's infinite is because we're counting events in a global description of the eternally inflating space-time. And what we've learned from black hole physics is that we should be extremely suspicious of the semi-classical approximation when it's applied to a region larger than one causal patch, larger than what one observer could in principle see. And when we restrict to one causal patch, the infinities disappear. So one approach that was advocated by Raphael is to simply regulate the infinities by restricting to one causal patch. This eliminates the infinities and also eliminates the attractor behavior that we were hoping to make use of. This may still be the right answer, but it's worth asking whether we can regulate the infinities while still retaining the attractor behavior. Now, of course, the right thing to do is to just compute the quantity in string theory and see if it's well defined. But as you know, that's not possible right now. So instead, we can hope that whatever the correct cutoff is, whatever the correct prescription is for computing this quantity, it reduces to something simple in the semi-classical limit, in regions where semi-classical physics is locally a good approximation. And so the program that we've been pursuing over the last few years is to simply guess a measure or a cutoff and derive its predictions and compare those to observation. Because this cutoff should be well defined throughout the multiverse in all kinds of vacua, it essentially has to be some kind of geometric prescription for regulating the infinite space-time volume. To be perfectly clear about the problem that we're attempting to address, this is what's often called the measure problem. A solution to the measure problem should take as input a semi-classical space-time or an ensemble of space-times or a set of rules for constructing the space-time. And it should compute for you NA over NB for any two events, A and B. Now, I think sometimes there's some confusion because we generally focus on a single semi-classical four-dimensional space-time. You could ask about various complications, like regions that are not four-dimensional, quantum mechanical ensembles of space-times, and all of these corrections do not substantially change the problem. So here I'm going to focus on the simplest setting where the problem arises, which is just a single eternally inflating four-dimensional space-time. Now, over the last several years, there's been a number of well-motivated proposals for how to regulate these infinities, far more than I've listed here. What's been exciting is that over the last few years, we've rejected several of these by comparison with observation. And we've discovered surprising dualities between apparently very different proposals. And that's left us with just a few viable proposals at this time. And I'm going to tell you about one of those. So my work on this subject culminated in 4 papers in 2010 with Raphael Busso, Stefan Leichenauer, and Vladimir Rosenhaus. And I'm going to tell you very brief highlights from that. One proposal for regulating the infinities, one success of this proposal, which is a robust explanation for why we observe the value of the cosmological constant that we see. I'm then going to tell you about one failure, which is a conflict with local physics and common sense. And it was the combination of a reasonable amount of success and this failure that bothered me that led me after this to try to look for new tools to approach this problem. So here's one proposal for a regulator. We're interested in regulating the infinite space-time volume. One way to do that is by simply drawing a red line at late times and only counting events before that time. There's a finite amount of volume before that line. Now, the idea is that this late time or infrared cutoff in the bulk should be derived from an ultraviolet cutoff in the CFT, in a way that we're familiar with from ADS-CFT. Concretely, if you picture the UV cutoff as some kind of lattice spacing on the boundary, which I've just denoted by these tick marks, then the rule is to only keep bulk events whose future light cones are larger than that lattice spacing. So for any finite UV cutoff, this defines some finite late time cutoff in the bulk. And then we can take the continuum limit, where the lattice spacing on the boundary gets shorter and shorter. So this is essentially a rule for defining a bulk time variable by relating it to RG flow in the boundary theory. Of course, we know very little about what this boundary theory might be, but I know enough to draw some tick marks on this diagram. So it should be clear from this that, again, this quantity I'm trying to compute is not what we would normally think of as a good quantum field theory quantity. If you're counting the number of events of some type, because of the exponential expansion, it's dominated by events that happen very close to the cutoff. That's why the answer is highly sensitive to what the cutoff is. So from the field theory point of view, this quantity, NA over NB, is dominated by physics very close to the cutoff scale. That's not normally the kind of quantity that we would like to compute in a renormalizable quantum field theory. However, the hints so far are that the theory on the boundary is something a bit more exotic than an honest quantum field theory, and it may well like to compute NA over NB, and so I'm going to proceed. Now, this cutoff proposal is not yet well defined. That's because this boundary metric, just as in ADS-CFT, is only defined up to the conformal factor. So we need to make we need to fix this ambiguity, because until I've decided what the boundary metric is, I don't know how to impose a uniform UV cutoff. This is where we have to make a guess, and our proposal is simply to fix this ambiguity by demanding that the curvature scalar on the boundary is a constant, and that the volume of the boundary is equal to some number, say 1. Now, some pretty math guarantees that you can always make this gauge choice, and generically this fixes the boundary metric completely. So having fixed this ambiguity, we now have a procedure for defining a bulk time variable by relating it to RG flow on the boundary, and this time variable we call it the new light cone time. So having chosen a time variable, we can now characterize the attractor behavior of eternal inflation. For small tunneling rates between vacua, just to give you a flavor for what sort of thing you could compute, you can compute the volume in each vacuum at late times. So for small tunneling rates, you can write a simple equation for how the volume in a given vacuum evolves. First of all, there's an exponential expansion due to the positive vacuum energy. Then there's some loss of volume due to decays to other vacua, and there's a gain in volume due to tunneling events into that vacuum. So it's a very simple equation, and if you have a toy model of the landscape, you can look at the dynamics of this. The solutions are exponential in time, and the late time behavior is dominated by the leading eigenvector, the solution that grows fastest with time. So the late time limit of the volume in one vacuum divided by the volume in another vacuum is independent of the initial conditions and controlled by this leading eigenvector. Because these decay rates are exponentials, they're typically quite different from one another. And in a broad range of examples, we can roughly think of this leading eigenvector as simply saying that at late times, all of the volume is in the longest lived de Sitter vacuum. That's simply an approximation to the exact form of the leading eigenvector here. Now, there's various issues about how well defined this proposal is. For example, if you have a region with negative cosmological constant, then instead of having this nice piece of future infinity up here, you have a singularity. When you have a singularity, it's no longer well motivated to think about a dual theory living on the boundary, and also this procedure breaks down. I'm not discussing this because this is the best defined measure proposals. There are better defined proposals. I'm discussing it here because I think it's a well motivated proposal. Now, when it is well defined, it turns out to be equivalent to just counting events in one causal patch. And you can kind of picture, this is true for a particular ensemble of causal patches, and you can picture it like this. If you have this entire global space-time, you can sprinkle points on future infinity uniformly using the metric that I've now fixed. Any point on future infinity defines a causal patch that's in the past of that point, and that defines an ensemble of causal patches. Okay, that's a bit abstract, but let me say it very concretely. And this is something that you can remember from this part of the talk. One proposal for regulating infinities derived from this UVIR connection is equivalent, approximately, to simply starting in the longest-lived de Sitter vacuum and only counting things within one causal patch. More precisely than starting in the longest-lived de Sitter vacuum, you should look at the leading eigenvector of this rate equation. So if you have any need to make predictions today, you can just go home and start using this prescription. It's extremely simple. And it's encouraging that the two clues we have, about how to approach this problem, one of them the UVIR connection, and another the idea of restricting to one causal patch, are consistent with each other. Regulating using UVIR gives us a simple description in terms of an ensemble of causal patches. Okay, so now let me come to one success of this approach, which is a robust explanation for the cosmological constant. We've made some improvements relative to the Weinberg prediction. The infinities are regulated in a well-motivated way, in a transparent way. There's better agreement with observation, and our argument is more robust. It's also 25 years later, and it's no longer a prediction. So the question I want to ask is, given that we live 13.7 billion years after our local Big Bang, what cosmological constant should we expect to observe? So I'm putting in the time when we live, but I'm allowing all other physics to vary. So I'm assuming that observers more or less like us can arise in a variety of different vacua with different cosmological constant. And in order to make a prediction, I need to count how many see each value of the cosmological constant. Now, of course, in principle, to do this precisely, I need a definition of what I mean by an observer. But as you'll see, this analysis is insensitive to that definition. Now, because I'm putting in T observer and holding it fixed, what I'm really addressing is the coincidence problem. Why do we live at the special time when the energy density in matter is comparable to the vacuum energy density? Or in other words, why is the cosmological constant related to the time when we're living in this way, when its natural value is much larger? I'm not addressing here, although we do speculate in our paper, about why the time when we're living is so large in Planck units. So I'm going to make this prediction by counting. I just need to count the number of observers who see different values of lambda. And remember that we're regulating the infinities by only counting things within one causal patch. So in order to count observers, I need two factors. First of all, I need the probability to nucleate a bubble with a given value of lambda. And then I need to count the number of observers inside that bubble within one causal patch. The number of observers I'm going to further divide into two pieces: the mass inside the causal patch at the time that the observers live, times the number of observers per unit mass. Okay, so far this is just math, but now let me treat these three factors in turn. So the probability to nucleate a bubble with a given cosmological constant is flat in the regime of interest for small cosmological constant. That's because, first of all, the nucleation rates are insensitive to the late-time cosmological constant. It's just not relevant at the energies where you nucleate the bubble. And also, the distribution of vacua is uniform near lambda equals 0 for vacua like ours, where the cosmological constant is accidentally small. All right, that deals with the first factor, which I'm setting to 1. Now, this last factor, the number of observers per unit mass, we're going to use an extremely simple model and pretend that this is independent of the cosmological constant. This completely ignores Weinberg's point that having a cosmological constant too large disrupts galaxy formation and makes it harder for observers to live there. The surprise is that we can get away with this gross approximation. So, having set 2 of these factors to 1, now I have a simple formula for the probability for seeing different values of the cosmological constant. It's just the mass inside the causal patch at the time that we're living as a function of the cosmological constant. And this I can compute using the FRW equation. So if you compute it, you find that there's 2 regimes. One regime is where the cosmological constant is small, where the cosmological constant dominates long after we live. In that case, the mass inside the causal patch just has a weak polynomial dependence on the cosmological constant. On the other hand, when the cosmological constant is large and dominates long before we live, then the amount of mass inside the causal patch is exponentially small. Now, this is a very simple fact, and I find that string theorists think probably a little too fast to try to understand something so simple. So try to slow down your brain. And what I'm telling you is a simple geometrical fact that the mass inside the causal patch is exponentially small at times long after the cosmological constant dominates. This is because the size of the causal patch is set by the cosmological constant, but the matter is exponentially inflated after the cosmological constant dominates. So this explains why we don't see a cosmological constant that's much larger that dominated a long time ago. It's because of this exponential suppression. There's no mass inside the causal patch, and so there's very few observers there. On the other hand, making the cosmological constant extra small requires extra tuning, and this factor of lambda to the -1/2 is not enough to push you in that direction. And so these 2 things together explain why we see a cosmological constant that's related to the timescale where we're living. In this argument, there's no detailed anthropic assumption like observers require galaxies or something like that, and it agrees very well with observation. Now, here's just a picture. So within this model, the formation of observers is completely undisturbed by the cosmological constant. But if the cosmological constant is small, then very few observers fit inside the causal patch. If the cosmological constant is large, then very few observers fit inside the causal patch. And if the cosmological constant is small, then the conformal diagram looks more like this. The causal patch is larger, and more observers fit inside. Okay, let me now come to a failure, which is unfortunately intimately connected with the success that I just talked about. This failure is not a conflict with observation, but it's a disagreement with common sense and local physics. Oh, and you're about to get to vote, so if you've been sending emails and stuff, you can just pay attention for 2 slides and your vote will be counted. So consider the following bizarre question that was first posed by Guth and Van Schuren. You flip a fair coin, and before you see the outcome of this coin flip, an experimenter puts you to sleep. And if this coin is heads, then you sleep for 1 minute. And if it's tails, then you sleep for 5 billion years. Now you wake up with no memory of how long you slept, and you're asked to bet whether you slept for a short time or a long time. Now, of course, common sense tells you, if this is a fair coin, that each thing is equally likely. But if you're doing this experiment in the multiverse, then we should be able to use our favorite formula for how to compute the probabilities. And you can see that if everybody's starting this experiment here on this blue line, we can just count how many people wake up after sleeping for a short time compared to a long time. And you can see that far more people slept for a short time. And so, if you ask about the magnitude of this effect, this is an order 1 effect on the timescale Hubble. So, we have a difficult choice to make. Either there are order 1 corrections to common sense on the timescale Hubble, or all of the geometric cutoffs are wrong. This is not something special to the cutoff that I've been talking about today. And now is your chance to vote so that I can bring the wisdom of the string theory community back to my measure colleagues, and then we can continue to ignore it. So the question that I want you to vote on is it acceptable to have this type of order 1 corrections on the timescale Hubble? Who votes yes, it is acceptable? Okay. Let's see, about 5. And who votes no, it is unacceptable? This is a pathetic display of cowardice. Okay. I have to say that my current view, and the reason that I have not been pushing forward the same type of approach, is that my view is that our cutoffs are too crude at this stage. And that the idea of restricting to one causal patch is the right idea, but this is too crude an implementation of complementarity. But it's far from clear. All right, so let me summarize then. So first of all, how to make real-world predictions is an important question. And I've advocated one proposal, which is to make probabilistic predictions from eternal inflation. This requires solving the measure problem. One measure that I've described is approximately the very simple rule that you should start in the longest-lived de Sitter vacuum, and you should only count things within one causal patch. This measure is successful at explaining the observed value of the cosmological constant in a robust way. But the same geometry which explains the observed value of the cosmological constant so well gives order 1 corrections to local physics on the timescale Hubble. Again, that's not an agreement with a disagreement with observation, but only with common sense. So if we're able to resolve this issue of complementarity, this issue of the conflict with common sense, there are many more quantitative tests as we learn more about the landscape. And these are potentially very exciting. Over the years, we've derived several non-trivial facts that have to be true about the landscape in order for these predictions to agree with observation. De Sitter vacua have to decay faster than a certain non-trivial bound. The tunneling rates to vacua with cosmological constant near 0 have certain properties. The tuning required for n e-foldings of slow roll inflation has to be only a polynomial in n and not exponential. There's a number of tests there. More generally, I think it's clear that we need 2 things in order to really make this idea convincing. 2 big things. One of them is a rigorous description of eternal inflation in string theory. The other is simply more predictions. And it would be very exciting to try to combine some of the hard work that we've heard about here in constructing models of particle physics with the dynamics of eternal inflation. As perhaps a more modest goal, I hope that a better understanding of complementarity could resolve the conflict that we're currently having with local physics. Thank you.
I'll take only one question. Yes, Betty.
Well, I just like to comment on the sleeper paradox. Depends how you pose a question. If you wake up and you have to determine probabilities of sleeping a minute or billions of years, you get one answer. If you wake up, ask at other participants who were given the same question, and you have to ask how many of them be in one state and how many in the other, you might get a very different answer according to which question you ask. And so geometric approach may look for the later, but makes no sense for the former. Now, I have no idea which question is right, but then I think until we sort that matter, we can't go any further.
Let's thank